Good afternoon, everybody. My name is Stuart Halloway, and I'm going to be talking to you about simulation testing. I'd like to start, though, by talking about some more familiar testing terms and techniques. I think the most common testing acronym, which you're probably all familiar with, is what are called example-based tests. And the idea behind example-based testing is you have some kind of setup where you sort of put the world into some sort of state where you're ready to go. So here, this is the canonical test-driven bowling example. Happens to be written in some non-closure language. And you set up your world, and then having set up the world, you have some inputs. In this case, we're going to bowl a 0, whatever that means in our domain. You have some execution that is used against those inputs. You have some output, and you have some validation of that output. Now, because this language doesn't have that nice parenthetical structure, you probably are having trouble reading and understanding what's going on. So I'll show you another example that is actually written in closure. So this is another example-based test. And this one's slightly different. It does sort of tip the hat to one of the advantages of programming in closure, which is that there's no setup. Right? There's no setup because this test happens to be a test of a pure function. So really the only setup is create universe. And then after that, you're able to test. But the rest of it kind of proceeds exactly as in the previous slide, even though it's written in a different language. You have inputs. You have execution against those inputs, which in this case is a lot of plussing. You have outputs. And you have validation of those outputs, which says the form on the left, when evaluated, x, ought to be equal to the form on the right, y. So most of you are probably used to writing these example-based tests. And so in the wild, there's a lot of terminology associated with this at different scales. You can have unit-level example-based tests or functional or acceptance, and there are probably a half dozen other trendy terms in the space. And there are styles to how you think about what you're doing and to the vocabulary you use, whether you're thinking in terms of testing or behavior. And there are common idioms for working in this style, setting up fixtures, stubbing out things you don't want to talk to right now, mocking things and being able to record interactions without actually interacting. So if you think about this style of testing and you deconstruct it, you have these common pieces. You have inputs, execution, outputs, and validation. And let's blow those apart. And let's talk about something that hides behind all of those things, which is a model of the world. In example-based testing, the model is in the developer's brain, which is a great place to keep it because it helps us all keep our jobs. But from a scalability or transfer of knowledge perspective, it may not be so great. And so the idea behind the model is this is not a model of the domain of your app. It's a model of the execution of your app. Right? So it's applying domain modeling to execution. It's saying things like, our customers are going to tend to show up in 3 different distinct profiles. There are the occasional browsers who come in as a result of some ad campaign. There are the seasonal customers, and then there are the zealous MyCo Prime shoppers who feel incentivized to come onto the site every day and see what's going on. And each of those profiles is going to have a different usage pattern. Likewise, our inventory, our delivery systems, all these things have characteristics that we can model. So the idea behind simulation testing is that you start by modeling these things. And these models tend to be statistical distributions of things and interactions between those things. And there's also this notion of agents in the system. So an agent could be a human user. It could be a proxy that represents an aggregate set of human users. It could be a process, right? It's anything that's going to generate novelty in the system while the system's running. Then you take that model and you use it through a program to generate a stream of inputs or streams of inputs. And so these are serialized by agent. So you might have, in your model, you might have chosen to say we're going to have 500 or 50,000 agents that we're going to use to simulate our system. And each one of those agents is going to have a time-stamped action stream. The agent is the unit of concurrency. So within an individual agent, things are serial. But then across multiple agents, things are concurrent. And you're going to store all that stuff in a database. Then there's going to be a driver program that's responsible for execution. And that driver program is itself going to be coordinated through a database, because databases have nice coordination mechanisms. And it's going to be responsible for mapping the agents onto processes. Every aspect of this aspires to work at different scales. So in the small, that mapping of agents to processes could be really degenerate. In fact, I'm going to work through an example at the REPL where all of the agents get mapped to one process. But the idea here is that you could scale this up hugely and have the agents spread across many processes. So this driver is going to execute the program. It's going to take actions on behalf of the various agents. And those actions are going to result in various kinds of outputs. Arguably, the most important kinds of outputs, typically in a system, are going to be kept in storage somewhere. So we interact with your system, and stuff goes into a database. But there are certainly other possible kinds of outputs. You could have logs. You could have metrics. Our goal in testing is going to be to roll up all these logs and metrics and outputs from the system as the user sees it, and put them all in a database as well, such that the validation step is implemented via database queries, which gives us the power of logic programming to think about how things are working in our system. So that's basically the idea. Now, Simulant is a library that I originally developed internally while testing Datomic, and it really makes heavy use of Clojure and Datomic. And there are a couple of design presumptions I made that are not necessarily good presumptions in general, and so I want to lay them out up front. So if you look at Clojure and Datomic and ClojureScript and Pedestal and other things that I've been involved with, there's an aspiration in all of those things to reach. Right? So Clojure is not written just so that we can all navel gaze in here. It's written to be a player in the JVM ecosystem at large. ClojureScript is not written just so that Clojure users can put things on the web. It's written so that anybody can put things on the web. I did not make that decision here. So there's no indirection in Simulant that's designed to be language agnostic. Right? This is about using Clojure. Likewise, I didn't put any indirection around the use of the database. This is about using Datomic. And the reason for that is that I wanted to utilize the power of both of these tools to the maximum possible extent. I will say now that everything I'm going to talk about you could do in other languages. You could do with other data stores, and I would encourage you to do so. I chose not to, and I just wanted to be clear about that up front. I wanted to get the maximum possible traction that I could out of tools that I was familiar with. So, Simulant starts with a schema. Everybody can read all that, right? So broadly speaking, it begins with a model. And the model schema has a few generic attributes. And then those generic attributes are extended or augmented by domain-specific attributes for the thing that you're trying to model. I'm going to show you a demo in a moment that has, it's the Hello World app that ships with Simulant that has traders. These traders are incredibly boring. They don't even have names. And they don't have different kinds of resources they trade. They have a single kind of resource. So they're essentially modeled as an entity that has a number associated with it. But every so often, they either give or receive that resource to others. And so to model these guys, there's some number of traders. They have a balance. They have some sort of frequency of trading and amount of trading that are expressed as statistical means. That model is then used to generate activity streams. And so an activity stream is a particular test is generated from the model. And this is an important step. We don't go straight from the model to the activity stream in some sense. This means that we can go back to the model and make a different test from it in the future. Notice that there are these simplifying separations being made every step along the way. So we can make a test from the model. We can come back later with more information and make a different test from the same model, or multiple different tests. Test consists of a collection of agents that represent the different participants in the simulation, and each of those agents has a time-stamped series of actions. I would note that it almost seems like when Clojure was designed, somebody had in mind this kind of use case when they named agents agents. I mean, it really is these agents are implemented with Clojure agents, and the fit is hand in glove. Right? Their job is to serialize execution, but you have a bunch of them, and they're all going sort of asynchronously with regard to one another. And again, there's a generic model that comes with Simulant, but then you're going to extend things onto these existing domain entities for your problem. So in this case, the agents have a transfer from, that's who's going to be doing the transfer, a transfer to, and a transfer amount. The sim also has a clock, and this is really important. One of the projects that Relevance is working on right now, that's used a little bit of simulation testing using Simulant, is going to eventually get into data sizes which are, shall we say, interesting for the hardware and software that they're running on. And so the idea is that we want to simulate that data size before we run it in production. Right? Most of us get to run simulation testing once. How do we do it? We ship. Right? We ship, and then we have these agents, and then they come along, and they generate concurrent activity, and we have troubles and whatnot. So the problem here is that we don't actually want to simulate the load at the speed that it's actually going to come in, because we know that in 6 months the data size is going to be interesting. If I run the simulation at that speed, then 6 months from now, the simulation will fall over with some bug, and production will fall over with the same bug, and that's not going to be so great. So the clock allows you to change the speed of time during the sim. There's also a model for managing the life cycle of various external systems. This is a very lightweight hook that provides just enough information for resource allocation and destruction in processes. And there is a model for the code basis of whatever you're doing. So we want to store with these tests how they got generated, what code went with them. Because if we have this, it's going to be great to have this data when we're done. We're going to run tests in this style. We're going to have all this data. We can come back and look at the data in the future. But if we have all that data and we want to reproduce something, and the code that we produced it with is forgotten to us, that's not so great. Fortunately, most of us are already using a nice value-based source code repository with content addressing. So we can just say, I generated this test from this model on this date from this get URI at this get shot. And then anybody else in the world can go and reproduce our findings. It sounds kind of like science that way. So now let's go do a little bit. So we're going to spend a little bit of time at the REPL. Except you have the window. No, I have the window. So the window on the top is an inferior Lisp buffer. This is what aging trolls who can't figure out how to get inREPL to run on their machine, but are going to get some help right after this session and learn how to do that, use. So apologies for not being fashionable. And in the bottom window is the Hello World example that comes with Simulant. So we're going to, and that's a little big. Is that still readable? How about that? No? Okay. Too far. So a lot of my projects now have a convenient macro that you can execute at the REPL. And basically, the simple stuff that Rich does is really cool. But every once in a while, I just want things close at hand. Instead of having all these wonderful Legos, I want a fully built house. And so convenient is sort of introduce the opinionatedness and gives you various names and scope and so forth. And then we're going to be simulating these traders. So we get some more namespaces. We don't really need to set the print length. And we are going to create an in-memory datomic database. I'm going to come back and talk about that choice at the end. So create an in-memory datomic database. And now we're going to load not one, but 3 schemas. We're going to load the schema that's associated with Simulant itself, right? That's the basic model that sort of stitches all those things together. Then we're going to load the schema for this sim. So this is a schema that describes the particular model that we have for how this thing's going to be used. And then, in this case, the system under test is actually itself a datomic-based system. So there's going to be a schema for it. And I want to just take a second here and talk about the cardinality fallacy. There's this fear when you see a lot of steps that something is complicated or a choose-a-phone or whatever. And it's really important that these steps are distinct. Could I have written a helper function for this demo that loaded all the schemas in one go? Would you think, it's probably, I know I'm not a great programmer, mostly a public speaker, but it's probably within my skills to have written a little function that would do all three of these things in one go. But the point of this kind of model, the point of sample app, the sample app itself, right, is a model. And the point of the sample app is to demonstrate the key ideas of the system, not to demonstrate how easy or fast it is to get started. So I'm deliberately breaking things apart here that you might well put together in certain contexts, depending on what you were doing. So now I'm going to create the model. And our model is going to make the following statements. We're going to have 100 traders trading concurrently. So that's going to be 100 agents probably, depending on how we convert it to the actual test. And those agents are each going to start with a balance of 1,000 pennies or whatever it is. We don't know. And they're going to, on average, trade 100 units when they trade. And they're going to, on average, trade once per hour. So that's our model of the world. This is tiny. This is a hello world model. A real model would have... for one thing, just having means is probably not good enough, right? It would be a mean against a particular distribution. So there's a lot of things that you could add here to flesh this out. And now we're going to create that model and stick it in the database. So transact it into Datomic and grab out the entity associated with that so we can see there that guy is. We're then going to create the test, which is the actual activity data associated with this. And when we create the test, this function is actually a multi-method that is driven by the type of the model and other stuff. So you can plug this in. It doesn't really matter how you do this because it's domain-specific how you get from the model to the test. I mean, Simulant doesn't really have a lot to say about it. I am going to say that we're going to make this particular test last 4 hours. Now I'm going to shrink the font size just a little bit and move some things around so you can see better. So now we're going to actually create the sim. So the sim, in this case, I'm using the noun sim to be the actual concrete run of a test. So from one model, we could generate n tests. From each of those n tests, we can run them again and again on different hardware, on different days, on so on and so forth. So I'm going to generate the sim. It's going to have 10 processes. So these processes are now operating system processes, hypothetically. So we're going to run this on 10 processes. I'm now going to store the code base. So this transaction is associating the trading test and the trading sim both with a particular point in Git, so that we can go back and say, we took the model and made a sim out of it at this Git SHA. We took the sim and made a test out of it at this Git SHA. And this is, in fact, a little bit creepy, because in terms of what I said before, there should really be 2 separate transactions here. Those are chronologically 2 distinct steps. So this is erring on the side of convenience versus really showing what would happen in a larger scenario. I'm also going to create an action log for the sim. I'm not going to tell you what that is yet. I'll come back in a minute. And I'm going to set the clock. Does anybody want to wait 4 hours to see the sim run? Okay, now I'm going to speed it up by a factor of 960. And then we're going to run the processes. And I actually started all 10 processes in this process. So process is intended to model OS processes, but there's no requirement of that. It's certainly convenient for testing your sim to know that you can do that all in one process. I'm now going to wait for this to finish. Anybody who can divide? Oh, we're done. That didn't take long. It finished while I was talking. Now we're going to grab values from the database. So we're going to grab the simulation database and the trading database. The trading database is our system under test. Right? That's the thing we want to make sure that it works. That's where traders interact and did stuff. The simulation database is the thing that recorded our model and our activity streams and so forth. And now we're going to do some data log queries to find out what happened. So this first data log query is going to say, given a test, find all its agents. Given the agent, find all their actions. And how many actions should there be? There's 100. It's 100 traders. They trade about once an hour for 4 hours. There should be 400. Should there be exactly 400? No. Okay, so that seems sound. 412, that seems reasonable. Now we're going to check the actions. So we're going to say, go and look, or actually the amounts of the actions. So go drill through test to action to the actual transfer amount. How many of these should there be? Kind of a trick question. It's almost the same query as before, right? Now we're just asking what are the amounts of all of them. There should still be 412 of these. And what should their mean be? Really close to 100. Okay. Now we're going to check the trades. So this query is, let's look, this query is against the trade database, whereas the queries before were against the simulation database. So we're going to check the trades. And this seems pretty humdrum, because there should be 412 of these, and their mean should be the same as the mean for the other. Right? The first thing was, these are the actions that we're going to take in the system. And now this query is saying, let's verify that those actions were taken. But in a larger system, there's going to be several interesting complicating factors. One of the things you're going to do is you're going to run these sims and you're going to unleash the chaos monkey. Right? So you're going to run one of your sims and you're going to unplug some machines during it. So when you do that, it's no longer going to be the case that all the things that you tried to do got done. Right? It's also not going to be the case in a non-trivial system, and in particular when users build up state over time, that there's going to be this direct mapping from what happened to what you get out. Right? It could be a lot more interesting than that. Right? Users have sessions over a long period of time. They interact in various ways. They change their mind. They retract things that they've said. Things get added and then subtracted. So this is very facile for a demo, but in the real world it could be much more interesting, which means you'd really want to have the power of a query language to be able to work with it. So now let's go find all the traders. And now we're getting somewhere interesting. The trader balances ought to add up to 100 times 1,000 when we're done. So this is a basic test that the concurrent properties of the application work. I'm really happy about this because it's datomic based and we talk a lot about transactions, so it would be awkward if they lost data or something like that. However, there's nothing magic about datomic that is going to know that trader balances aren't supposed to go negative. I know because I wrote the sample app that I had in my mind that the balances shouldn't go negative, but I didn't do anything about it. So how many traders are going to have a negative balance? I don't know. But there shouldn't be any, but there's one. Right? So we have this system by design for this demo has a bug in it. Right? That you could now go back and fix and run the simulation again and see if that goes away. Now, let me come back to where did it go? I said before that this sim was going to have the action log in it as well. The idea behind the action log, and those that were in Zach's talk yesterday, it's similar to that stuff. The idea behind the action log is that you want to capture additional data about the execution that's not normally captured as part of ordinary program execution. You could do that by traversing metrics or logs that you produce already. In this case, the sim has a fairly lightweight built-in ability to capture information about actions. And so now we can go back and say things like, where are we? I'm going to have some data log rules, and I'll be able to say things like, the trade times should match the counts of all trades, and the mean trade times. So what's this doing? This is saying go and find all the actions, and then there's a data model associated with that action log that would let you pull out for each action how many nanoseconds it took. So that all gets recorded and placed in the database as well. So you pull that out, and now we can say we have a requirement that the mean trade time be less than 20 milliseconds. Now, in all probability, that's not actually an interesting or sophisticated requirement. It's probably something more like 99.9% of the request should complete in less than 20 milliseconds. But this is a really, really fast system because it runs in memory, so all the trades are actually completing, or the mean is sub-millisecond. It's about 400 microseconds to do these trades. What I just showed you showed everything being done in one process. It showed everything being done serially by one person at one time. Every one of those points, though, modeling, making the test data, running the simulation, and validation can be split chronologically. Right? You could separate those across time. Those could be done by different teams. One of the interesting scenarios here is you get a call from a customer saying, I'm having a bug where I see symptom X. And you slap your head and you say, oh, yeah, we never even thought about symptom X. We never, now that you say that, I can totally imagine how that could be happening. What do you have to do to reproduce their bug? You don't have to set up a simulation. All you have to do is run a query against the simulation that you ran last month, right? You write a new query. They call in and they say, after 6 weeks of operation, this kind of thing happens. Well, you've had sims running for months and years and whatever. You go back and say, okay, I'll go back and run a query against the outputs. And so you say, okay, I just reproduced it. And then the other side of the phone is like, huh? How did you produce six months of load and reproduce that? Well, you already did that part of the work. By creating these temporal join points in the way you model the system, you get a lot of power. Now, I want to talk for a few minutes about underpinning technologies here and some things that are used typically in conjunction with simulation or inside of simulation. One of them is the contrib library data.generators. So data.generators itself got refactored out of closure test generative. And the job of data generators is to do a couple of things. Its job is to generate all kinds of data. Generating all kinds of data is a horrific pain in the ass in OO, because every new project in OO creates new kinds of objects, which means you don't a priori have a way to generate that data. But Clojure is super beautiful for this, right? Because how many kinds of data are there? Right? There's this very limited set of things. So I can actually say, I'm going to get up one morning and say, I'm going to write a program that knows how to generate all kinds of data. There's actually a generator in Clojure data generators called anything. And if you call it, it will give you something, right? It will. It'll give you, it might be a list, it might be a vector of maps. It actually can't generate anything. It deliberately does not generate nested collections of collections of collections, but it could have been written to do that. You want to be able to have various distributions, so you don't want to have just uniform distributions, although I'm a statistics wimp, so I often use uniform distributions. You want it to be predictable. So the big deal here is that you want to have random engines that you can seed in such a way that you can go back and say, I want to do this again exactly like I did it before. So the implementation approach for this is that the generator functions in Clojure data generators shadow functions with similar names in Clojure core. So there's a function named long that makes longs. There's a function named short that makes shorts, so on. And the default integer distributions are uniform on range, right? The word long doesn't tell you anything about the distribution of longs. And then there are, and likewise, there are kind of arbitrary defaults. So if you say, make me a vector of strings, you haven't said anything about how big the vector is going to be. You haven't said what you want the strings to look like. Those defaults are fairly arbitrary, but you can add your own additional capability there. And there's a dynamic binding of rand on every thread, so you can repeatably generate things by controlling that guy. So here's what that looks like. The scalar generators, gen short, well, first off, gen is the idiomatic prefix, so if you're using it, if you want to be cool, make that your prefix. Gen short is going to choose a value uniformly from the range of short on your local platform. Gen uniform lets you take control. So this is saying I want something from 0 to 10. And RandInt, it's like, well, wait a minute, why do I need RandInt? Clojure already has that. Well, you need this RandInt because Clojure's RandInt doesn't give you any control over the seed. So one of the things that I did wrong in the first implementation of this was I leveraged the Clojure rand stuff whenever I could, and that just stopped my ability to be predictable. So the collection generators, again, if I say give me a list of shorts, the default size of that list is fairly small. It's not 5. There's actually a sizer. It's a geometric distribution. I can't remember the parameter. I picked something that doesn't make things that are likely to exhaust memory when you ask for default things. But you can then say, by passing in an explicit number or a function that returns a number, make me a collection of a particular size. So this says make me a hash map from shorts to strings of size 2. This could have been make me a hash map of shorts to strings of gen uniform 0 a million, and then you get a different distribution. And then, of course, you can compose these things together. So gen one of gives you one selected at random with equal weight from other generators. Gen weighted lets you choose weights. So prefer here to give me longs, but every once in a while give me a keyword. And then there are the sort of wrap-up ones, which are more goofy than useful. But gen scalar says give me any possible Clojure scalar type. And gen collection says give me any possible collection. In this case, it happened to pick a set of longs, it looks like. So weights, any scalar, any collection. And there's one, the implementation of gen anything is gen one of, gen scalar, gen collection. Right? So it does give you, it has all these biases built in, which you'd have to tweak for your own self, right? Because you might think generating anything should have a lot more scalars than half of the things being scalars. You can do all that. The other library that you're not necessarily going to use directly while you're using Simulant, but you might, is test generative. And the objectives of test generative are to be able to generate test inputs, duh, and to simplify data generation, execution, and validation. So this is very similar to Simulant's goals, but with one thing missing. Right? Test generative does not aspire to sort of break things out across time and put things in a database. So this is for typically a smaller scoped kind of testing, but it still wants to say, I want to separate generation, execution, and validation. I want to then be able to provide knobs for intensity and duration. I love this about generative test suites. Instead of, my test suite takes 5 minutes to run, or my test suite takes 10 minutes to run, I tell it how long to run. Right? Go run for 6 hours and use 2 threads and let me know how it goes. It needs to produce and consume data. This is super important. And it needs to play well with others. So I'd like for test generative, because it has a runner in it, to play well with other test frameworks. The approach then that's taken in test generative is that tests are infinite data structures. There's a runner that executes tests and makes events. Handlers process those events. Again, people that were in Zach's talk, there's a ton of overlap here, and there's probably a lot of good ideas that he was talking about yesterday that would fit into this model. And then the part that you actually see at the top, which is a DSL made with a macro called defspec, is by far the least interesting and important thing. When Rich was talking earlier in the conference about things for programmatic consumption and things for human consumption or user consumption, right? All the design in this is the part underneath for programmatic consumption. And then there's this DSL at the very top for human consumption, but it's built cleanly out of those other parts. So here's a picture of kind of the whole thing. The runner takes tests, which are data structures, and it also takes closure.test tests. That's my way to try to trick you into start using it. It takes closure.test as an arbitrary just extension that's not really related to the functionality of the tool, and some configuration. And then as the test runs, it produces that tall thing in the middle, which is an event, which is a data structure that doesn't have all those fields in every case, but could have any of those fields or additional fields. The white fields are fairly generic to any kind of test. The bluish fields are specific to generative tests, and whatever that color is. What does that look like to you? Mustard. The mustard fields are closure test related events. And then all those events are piped to different handlers. And so right now there's a handler that does pprint, which is really overwhelming when you run it, because it's producing these events like with a generative test per every generated input, execution, and output. There's IO console, which waters this all down to little dots, going by on your screen. So how many people have run the closure test suite? Anybody ever run the closure? When you run, you should do that, by the way, when you submit patches. When you run the closure test suite, those dots are actually all that data being dumbed down to dots. So if you want to, you can switch that default and have it do a ton of more stuff. I think it would be really interesting for someone to take this data and pipe it to Riemann, or pipe it to Storm, or pipe it to Datomic, or other places that have data processing or data storage capabilities. So I'm not going to talk through the entire. There's slides here that talk more about test generative, but I'm going to not do that and jump ahead a little bit, because I want to talk about how Clojure and Datomic really help make Simulant work. So on the Clojure side, there's a huge win to be had using multi-methods. There are no objects anywhere in Simulant, but there's a ton of polymorphism. And the polymorphism is accomplished without ever realizing anything that's polymorphic in the Java sense. And the way that's done is through keywords that are in the database. Right? So there's information in the database that's sufficient to drive the polymorphism, which means, and this alludes to a talk from yesterday as well, that the model really goes all the way from the database to the front of the world. Right? There's not an impedance mismatch when you switch over when you're working with this. Seeks and laziness are really big for making a long-running thing that is going to be bigger than the memory of any one process. And then agents were huge in implementing this. It was really just like somebody thought they wanted to make simulation testing when they created agents or something. So this is a database app with multiple layers that has called out different things that multiple teams could work on. It has all these capabilities. How much code? 700 lines of code for the whole thing, which I think is pretty cool. A secret about Rich that I'll tell you guys, his abilities are limited. He can't make anything that has more than 500 lines of code in a file. So he refuses to design anything that'll take more than 500 lines of code. So you'll never find out what could happen if he wrote 1,000 lines of code in a file. This is not all in one file, though. So he might have written it, but he didn't. And then on the datomic side, it's a really big win to have open schema, because Simulant is able to lay out a model that says there are all these pieces that work together like this, and then you can come on and add to all those pieces. Imagine what that would be like in a relational database. How would you do it? Right? You'd have to make new one-to-one join tables all over the place. It would be totally icky. And then you would do object relational mapping to hide yourself from the details of it. It would just be really gross. Datalog is really terrific in having access to the queries in the browser. And again, having that model extend all the way from the data side up to the user side. Having a time model is obviously a big aspect of thinking about how to do things in Clojure in general, and it really pays us back well here because we're able to break apart tasks over time. And multi-database queries is big. I want to have all those different phases in simulation testing in databases, but I don't necessarily want to put them all in the same database. And so the fact that datomic queries can join across different databases and actually have real hash joins and so forth with multiple different data sources really facilitates the style of programming that's used to build Simulant. So, what does it take for you to start using this? The first thing it takes is for Bobby Calderwood or me to go and throw it up on Clojars, which is happening now-ish. Yeah, so it's already, there's a GitHub repository. It's on the Datomic GitHub repository, so you could download it. The relevance guys who are already using it on projects are really going to be happy that we give them a Clojar's reachable target. They're tired of embedding the source code in their projects, so I'm going to get a big hug after this, I'm hoping. If you're thinking about adopting this, the first thing I would say is you can test any target system. I show testing Datomic with Simulant because that's actually what I do. That's my day job, is testing Datomic with Simulant. But you could use this test, you could use Simulant to test any kind of system. Right? If you're using it to test your own system, then it's going to be on you to figure out how to get your data out and ask questions about it and so forth, obviously. The other thing I would say is I'm not a hater. Right? Don't throw out your example-based tests. If you have an existing testing approach that works, I mean, the Clojure community doesn't believe in throwing out anything. You'll notice that our data structures only grow. The same is true here, right? Don't throw away the way you're working today. The third thing I would say is that while I think simulation testing aspires to be and my implementation is doing a, B- job of being simple, simple doesn't mean easy or convenient. You're going to get calluses, and it's going to take you about a week to develop those calluses. That's experience from relevance people picking it up and using it on projects. It was like in day one, like, why am I doing this again? And on day 5, it's like, okay, I sort of get it. And on day plus 20, it's like, oh, this thing just found a bug that I don't know how we would have ever found any other way by realistically executing our program. And finally, I would say that simulation requires time and thought. The interesting part is not the typing in code. The interesting part is not the typing in data schema. The interesting part is modeling. It's that when we exploded the different pieces of testing, it's thinking about that and being explicit and saying, who's going to walk up to our system, right? And so, for example, if you're a person who is perfectly willing to have multi-hour arguments about performance in a bar with your coding buddies, but you've never actually enumerated performance requirements on a project and actually try to adhere to them and test for them, then this is going to feel like really from outer space, because it's definitely in the on the science side of that thing. We're not going to sit around in bars and argue about how the system works. We're going to simulate how the system works and learn from that. There are references available online, and the best way to get them is to go to my GitHub repository, which has the slides from this presentation and the slides from all of my other presentations. And if you'd like to have me present at your company or at an event near you, you can ping me at Stuart Halloway. And I think, am I at time? Nah. All right, well, I'll take a few questions. Surely there must be questions. Yes?
What kind of bugs do you work well for this? What kind of things are good at catching?
So are you asking this question in the spirit of you want to start producing a certain kind of bugs? So obviously, you're not. This would be a sledgehammer to test the things that you would normally catch with unit testing or REPL development. right? And I'm not really worried about those kinds of bugs because REPL development and a little bit of example-based testing really catches those. This is really a matter of calling out, I have a complete misconception about how I'm using this API. I have a complete misconception about how my system works. And if you think about it, these tests, a lot of times unit testing and even REPL interaction, if you've misconceived something, you're too close to it. Those two things are too close in time and space. So you make the mistake and you make the same mistake in your test, right? And your test is now actually kind of evil because it's actually reifying your mistake and giving weight to it and blessing it. And this is really coming back later and saying things like, what are characteristics our system should have, right? If these are the kinds of load, should we expect to have spikes? And then if you do have a spike, it's like, oh, you know what? We've overwhelmed JVM RAM, and we're in garbage collection hell on this box. Right? You're not gonna find the kind of problems that plague systems in operation. This is also the only kind of testing I think that has much chance of catching misconceptions. Right? I don't think that example-based testing has almost any chance of catching misconceptions unless it's performed by entirely separate people than the people who wrote the code in his black box. Right? Because if you have that misconception in your head, you have it in your head. You're already screwed. Whereas this kind of testing is really coming in after the fact and has a chance to really do that. As an example of that, when I was writing the Hello World application, I incorrectly wrote a datomic query in such a way that things got collapsed into a set. A set of things in the query got collapsed to a single value because that's how set-based things are going to work. That's not what I wanted. Right? So what happened was if two events had exactly the same number of milliseconds that they took, because I wasn't pulling milliseconds back from the query, they got folded down to one result, and some of the numbers were being discarded. Right? There's no way I would have caught that in a traditional test, but by looking at what was happening in the data, it quickly became obvious. Right? The distributions were skewed, and the counts were wrong. It's like, okay, what would be a possible theory? Right? Query must be broken. Well, it turns out query wasn't broken. My use of query was broken. Other questions? Yes? So the question is, benefit Greenfield versus benefit existing complex system. I think one of the biggest problem with testing a complex system that isn't well tested already is that it's going to uncover all kinds of problems with the API and use of the system because it was never designed for testability. So it doesn't have the seams and join points where you would want to probe things. So adding those probes is a high value thing. If you look at like Michael Feather's book, Working with Legacy Code, he talks about breaking into existing code bases and putting that stuff in. So my expectation is if you have a code base that you don't think is well tested, you're going to have a lot of misery adding this. Not that it's a bad idea, but you're going to have a lot of misery doing it. The other thing is that being really careful to leave out those last little shims of mutability and those last little shims of realization of UI. One of the key ideas in Pedestal that you guys saw earlier is to leave a lot of things testable just at the data structure level. And then, there's seams in Pedestal such that you can write unit tests that are testing all the logic and flow through your application except that last little bit of rendering. And the only way you're going to test that last little bit of rendering is by looking at it anyway. Right? So having those kinds of seams is really important. Trying to test like this is going to force you or encourage you to put those kinds of seams into your application. I actually would argue that if you went through the planning exercise of devising the model as a data structure and then threw it away and didn't do this testing at all, that would be valuable. Right? If you just did that model, what's that?
That's what the bug is.
Well, yeah, right? So, and it's much cheaper, right? It's incredibly cheaper to look at that model. And if you sit down with your stakeholders and say, we're going to make a model of how the system is going to use, if you've never done this before, I guarantee you that someone's going to walk up at some point and go, that is completely wrong. Right? You said that 60% of the users are going to be like that, but that's not true at all. Right? At most 5% of the users are going to be like that. So the observation is it works in the small, and I would even go so far to say that it works in the tiny, right? So the example that I gave is all in one file, in one interactive session at the REPL that did all those different pieces. The ability to run the entire sim at a tiny scale like that is really good for testing because the sim itself needs to be testing. And I want to underline that. My tests have tests, right? Right? The sim itself, right, is a complicated beast, potentially, right? It does a lot of interesting stuff. And so you're going to want to make sure. Now, one of the things that's great about the sim is that the different moving parts act as kind of checks and balances for each other. And so there's some testing that's built in just in sort of getting the sim to run at all. gives you a certain kind of first baseness about how your system is working. Yes?
Does Simulant have an opinion about how to do validation, or is it potentially kind of open-ended?
Simulant does not have an opinion about how to do validation other than that all these different pieces should be in a database and should be kept over time so that you can go back and do that. Most of the validation that I've done has been in data log or just straight up functional closure code traversing entities, but you could certainly attach core logic to this and do logic-based, whatever you want to do. I mean, it's in a database. You could write mutable imperative validation loops. I wouldn't strongly encourage doing a lot of that. But yeah, there's not an opinion about how validation is going to be done. And there's no, that 700 lines doesn't include any sophistication about statistics. So if you watch was Edmund Jackson's talk at ClojureConj last year, right? Applying math head techniques beyond what's in there, which is almost none, is certainly the kind of thing you can do having a database and a query language at your disposal. Yeah, so the observation is that there's a cognitive element to getting you engaged with thinking about how your users are going to interact and modeling that. And I would underline again and again and again that having the temporal separation between these steps means that you can make models that you don't know how to convert into action streams, right? That might be a valuable thing, even if you don't currently have the know-how. Or you can have really wimpy validations, and when you have better validations 2 weeks from now, you can go back and run them against your past execution runs. Right? That's the excuse I always use when I'm talking to Rich about the tests I've written for Datomic so far. I'm like, yeah, I'm going to make the validations stronger later in the future. One more question, yeah. So the time scaling, the question is, how do we make the time scaling stuff work? So there's two levels, and maybe there's additional levels in between. The level that's supported here is that the time is all relative time, and and the clock is a multi-method. So right now, it's relative time, and the knob gets turned only once at the start of the simulation. So it's incredibly stupid. A slightly smarter version would be able to make that like a time that changes throughout the sim, but was relative. But what you really want when you go hardcore with this stuff is to have the time be absolute, which means actually changing the clock time on all the processes. And so the system that Rich worked on, which my conversations with him about were the inspiration for Simulant, they actually did that. Right? They went the whole 9 yards and were actually setting the system clocks, and they had a time server, and everybody was getting time from the time server throughout the sim, and the time server, you could turn the knobs on it. So if anybody wants to submit a patch for that, that'd be fine. So, I mean, part of the problem there is that it's not just a closure problem, right? I mean, it really is it spans whatever kind of devices that you're actually using on your system. I mean, how far are you going to go? If you're testing mobile endpoints, are you going to set the clocks on those? You could, maybe. All right, I will be out back if anybody has more questions, or up top or wherever that is. Thanks very much. I really appreciate being able to be here.